Welcome to AI Paper Podcasts. Today we're tearing into a brand new paper from Peking University in ByteDance titled Enhancing Spatial Understanding in Image Generation via Reward Modeling.
If you build or fine-tune text-to-image models, you already know the bottleneck. Current models produce stunning aesthetics, but they completely fall apart when you ask for complex spatial relationships, like placing specific objects left, right, in front, or behind each other.
Current reward models and even massive VLMs like GPT-5 just constantly hallucinate here. They simply fail to evaluate spatial correctness accurately when chaining multiple objects.
To solve this, the authors introduced a three-step fix. First is the SpatialReward-Dataset. That's 80,000 expertly curated adversarial preference pairs.
Second is SpatialScore, a specialized 7 billion parameter reward model that actually outperforms GPT-5 and Gemini 2.5 Pro on spatial evaluation.
And third is RL optimization. They apply this reward model using GRPO with a novel top-scale filtering trick to train base models to finally understand space.
All right, let's unpack this for you, our fellow ML engineers and AI researchers tuning in. I mean, we all know the pain of prompt engineering a diffusion model. You want a highly specific scene, you type it out, and the model gives you something that looks beautiful.
Yeah, it might win an award for lighting and texture.
Right, but it completely ignored where you told it to put the objects. The paper uses a really great specific example for this bottleneck. Imagine you prompt a model with a bright yellow surfboard, a striped beach towel in front, a bucket to the left, and a red ball to the right.
To a human reader, that is a perfectly straightforward scene. You can close your eyes and map it out instantly. But mathematically mapping those distinct semantic tokens to precise spatial coordinates across a latent space, it's an incredibly difficult task for a diffusion model.
Because the cross-attention layers just kind of...
They blend concepts together, exactly. They might attach the yellow token to the towel, or they might just cluster all the objects in the center of the frame because that's what the training data typically looks like.
I get that, but what really stands out to me here is that the authors don't just point the finger at the generative architectures themselves.
No. They trace the failure upstream to the evaluation metrics and the reward models we use to train these systems. If you're doing online reinforcement learning, your policy model is only ever as good as the reward signal guiding it.
If the signal is flawed, the model optimizes for the flaws.
Precisely. Let's look at those flawed signals, because our existing tools are basically asleep at the wheel with spatial logic. Take human preference models first. Things like PickScore, HPSv3, or image reward.
Why are they leading us astray for spatial alignment? Is it just human nature?
It totally comes down to human psychology. Those datasets were built by crowdsourced workers clicking on whichever image they liked best.
Humans are drawn to pretty pictures.
Right. We look at the vibe.
Yeah, the lighting, the resolution, the overall aesthetic. The evaluator gives it a high score and glosses right over the fact that the bucket is on the wrong side of the towel, or that the shovel is missing entirely. So when you use PickScore to guide your RL loop, you're inadvertently teaching your model to prioritize looking like a professional photograph over following the actual instructions.
Exactly. The paper has these crazy graphs showing models assigning higher reward values to spatially incorrect images than correct ones, just because the wrong one had better cinematic lighting.
Which sounds like an absolute nightmare if you're trying to build a reliable system for enterprise use. But what about rule-based benchmarks? We don't have to rely on human vibes.
You're thinking of things like GenEval.
Yeah, GenEval. It uses object detectors to check if things are placed where the prompt dictated. On paper, a hard-coded object detector seems like a foolproof engineering fix.
It seems foolproof until you run into the realities of computer vision, specifically occlusion. GenEval relies on relatively simple bounding box object detectors, and the paper highlights a very telling failure case.
The banana prompt.
Yes, the bananas. The authors prompted a model to generate 2 bananas. The image clearly shows 2, but one is slightly behind the other, partially occluding it.
So a human sees 2 bananas.
A modern vision language model sees 2. But the rigid object detector that GenEval uses completely failed due to the visual overlap. It threw an error stating expected bananas equals 2, found 1.
Oh, wow. So a single occlusion error completely ruins the reward calculation for that training step.
And occlusion is just the start. Wait until you throw a long chain prompt at it. GenEval was designed for simple binary templates, like A is to the left of B.
But when you chain them, like the bucket is left to the towel, which is in front of the surfboard, while the ball is right.
It breaks down entirely. It cannot parse the compositional diversity or the depth of the scene. It just isn't sophisticated enough to act as a reliable reward signal.
Okay, so human preference models are distracted by shiny things. Rule-based detectors are fooled by a banana hiding behind another banana. That brings us to the modern AI developer's favorite solution.
Just throwing a massive API at it.
Right. Why not just plug the latest proprietary API or a huge open source model like Qwen 2.5 VL72B in as the judge? We have trillion parameter models passing the bar exam. Surely they know left from right.
You would really think so. But relying on massive, generalized VLMs introduces two huge bottlenecks: cost and reliability. Think about online RL mechanics. You are querying the reward model thousands, potentially millions of times during a single training run.
Pinging an API like GPT-4o for every single generated image across a batch is just...
It's prohibitively expensive. Plus, the network latency makes a practical training loop impossible. But even if we ignore the API costs and host a state-of-the-art 72 billion parameter model locally, they found a surprising limitation.
They still hallucinate.
Heavily. They suffer from substantial hallucinations when reasoning about complex spatial relationships across multiple objects. They're incredible at general reasoning, but just not optimized for the highly specific niche of multi-object geometry.
Which brings us to the core thesis of this deep dive. If you want to do reinforcement learning correctly, you cannot rely on generalized tools. You need a flawless, highly targeted reward signal.
And that's where the researchers decided to build their own ground truth from scratch, the Spatial Reward-Dataset.
This is where the methodology gets incredibly practical for anyone listening who works on data pipelines. They didn't just scrape more data. They engineered 80,000 highly specific adversarial preference pairs.
The concept of an adversarial pair is the secret sauce here. For every prompt, they have a perfect image that adheres strictly to all the spatial relationships requested.
And a perturbed image.
Right, which looks almost identical in terms of aesthetics and objects, but slightly violates one or more specific spatial relations.
Just to paint this picture for you, think about how subtle these pairs are. The prompt asks for a home office. Desk-centered, laptop in the middle, mouse to the right of the laptop, notepad to the left. The perfect image nails it.
The perturbed image features the exact same aesthetic, same wooden desk, same cinematic lighting, same laptop. The mouse is on the left and the notepad is on the right.
So it forces the reward model to actually look at the spatial geometry.
Exactly. Rather than just doing a semantic checklist to confirm that a laptop, mouse, and notepad simply exist in a nice-looking room, it isolates the spatial variable completely.
There's another vivid example in the dataset. A kitchen stovetop, a kettle on the left burner, and a frying pan on the right. The perturbed image simply flips their positions.
It is such a minor semantic change. But for a model trying to learn left from right, it's the entire ballgame. Creating 80,000 pairs like this is a monumental effort.
But the quality control is what makes it work.
Yes, every single pair was carefully reviewed and filtered by human experts. They didn't just trust a script to generate the perturbations and assume they were logically sound. They gave annotators strict guidelines.
Because if your reward model learns from noisy data in RLHF, that noise just compounds.
Exponentially. You end up with a policy model that learns to game the noise rather than solving the actual task.
So by meticulously curating this adversarial data set, they laid the foundation for SpatialScore, the custom reward model based on the Qwen 2.5 VL architecture.
And the ablation studies they ran on scaling this model are fascinating.
Right. They scaled the backbone from 3 billion up to 7 billion parameters. In a world of trillion parameter models, is a 7B judge actually big enough to catch these subtle errors?
The jump in performance from that specific scale-up is remarkable. When they moved to the 7 billion parameter version, the pairwise prediction accuracy jumped from 89.1% to an incredible 95.8%.
Wow. How does a 95.8% accuracy on a specialized 7B model hold up against the frontier models?
It actually beats them. This specialized 7 billion parameter SpatialScore model surpasses massive, general-purpose proprietary models like GPT-5 and Gemini 2.5 Pro, specifically on this spatial understanding task.
That is the ultimate takeaway for ML engineers listening. Stop throwing API credits at generalized models for niche evaluation problems.
Exactly. The paper proves that highly targeted, expertly curated data trumps sheer parameter scale for reasoning tasks. A generalized massive model has its weights distributed across a vast latent space. It has to write Python code and summarize Shakespeare.
But a 7 billion parameter model fine-tuned exclusively on expert spatial pairs becomes an absolute savant at that one task.
Taking the time to build perfect adversarial pairs yields a better, cheaper, and faster local evaluator than any generalized API ever could.
All right, so we have a flawless data set. We have SpatialScore punching way above its weight class. Now we have to actually apply it to the base text-to-image model using online RL.
They use a framework called GRPO, or Group Relative Policy Optimization.
But they hit a mathematical hurdle they call advantage bias. To understand that, we should explain why they're using GRPO instead of standard PPO in the first place.
GRPO has become incredibly popular in the open weight community because of hardware constraints. Standard PPO requires maintaining a critic or value model in memory alongside your policy and reward models.
Which eats up massive amounts of VRAM.
Exactly. GRPO eliminates the need for that separate value model. For a given prompt, the policy model generates a group of images. The reward model scores them all. Then GRPO normalizes those scores against the group, meaning to calculate an advantage for each image.
Pushing the model toward images with a positive advantage and away from the negative ones, it sounds like a brilliant way to save VRAM.
It is, but what happens when the prompt is easy and the model does a great job right out of the gate? That is where advantage bias rears its head.
Oh, this is a great quirk of RL math. Let's put some numbers to it. Say you have an easy prompt. The model generates synced images, and they are all high quality and spatially correct.
So our SpatialScore judge evaluates them and gives them all high scores, say an 8, 2 7s, a 6, and a 5.
But GRPO normalizes those rewards against the average of that specific group. So perfectly good images that scored a 6 or a 5 end up getting assigned a negative advantage score.
You are literally penalizing the model for getting it right.
Just because it wasn't the absolute highest score in an already excellent batch?
Precisely.
Yeah.
The mathematical formula for advantage normalizes the variance. If the variance is low but the mean is high, slight deviations become huge negative penalties. You teach the model to avoid behaviors that actually produce correct layouts,
which introduces massive instability. So their solution is top K filtering. How does filtering the group solve that mathematical penalty?
by restoring a balanced sampling ratio. If they sample 24 images for a prompt, they don't feed all 24 into the GRPO advantage calculation. They select only the top K and the bottom K images.
Say K is 4. You take the 4 absolute best and the 4 absolute worst from the batch of 24 and only compute relative advantage on those 8.
That ensures you are always comparing clear winners to clear losers, completely eliminating that noisy middle ground.
Where good images get unfairly penalized. But beyond stability, there's a huge compute benefit here regarding NFE, the number of function evaluations.
To put this in perspective, for anyone managing a compute budget, NFE dictates how long your training loop takes. It's the number of forward passes the policy model has to make during the training stage.
And modern base models like Flux are flow matching models requiring multiple denoising steps.
Right. Let's say we use 6 denoising steps. If you use standard GRPO without filtering and sample 24 images, your NFE is 24 multiplied by 6 per prompt for every single step.
That's 144 forward passes.
Which will bottleneck your VRAM and explode your GPU hours. But with top K filtering, if K is 4, you only pass 8 samples through the training stage.
So 8 multiplied by 6 is just 48 forward passes.
You're slashing your forward passes by 2/3 per step. That is the difference between your training loop taking a week on an H100 cluster versus finishing over a weekend. It keeps online RL highly efficient.
Let's talk empirical results. They've got the adversarial data, the specialized judge, and the top K GRPO optimization. They compared their SpatialScore trained model against a baseline Flux.1 dev model trained using standard flow GRPO on the generable benchmark.
This comparison perfectly illustrates what happens when you optimize on a flawed rule-based benchmark versus a specialized reward model. It highlights classic reward hacking.
The forgetting problem. The visual proof in the paper is striking. When you train the Flux model using the flawed general benchmark, it actually loses its ability to follow long, complex prompts entirely.
Because General only checks simple relationships. A left of B. The policy model finds the path of least resistance. It learns it can get a high reward just by plopping down object A and object B and ignores the rest of the prompt.
Because rendering objects C, D, and D adds risk without adding reward.
So it just stops generating them. There's a perfect example of this. The prompt is a detailed dining room scene. A sideboard holds a platter, a tall candlestick to the left, a short candlestick to the right, grapes behind the platter, and bread in front.
When you look at the baseline flux model trained on Geneval, it's a disaster. It has a platter and bread, but completely forgot the candlesticks and the bowl of grapes. It just gave up on the complexity.
Contrast that with the model trained with SpatialScore using top K GRPO. It's a revelation. Every detail is present and accurate. The tall candlestick is left, short is right, grapes behind, bread in front.
It maintains the high visual fidelity while perfectly nailing the spatial layout. There's another image that caught my eye. A red car is centered. A blue car is parked behind the red car slightly to its left. A shopping cart stands in front of the red car toward its right.
The SpatialScore model gets the occlusion, the depth, and the positioning absolutely flawless.
It's like the model finally understands the 3D geometry of the scene it's rendering in a 2D space.
And that is the true achievement here. They haven't just taught the model to memorize compositional templates. The rigorous RL process embedded a stronger sense of spatial reasoning into the latent space itself.
Let's synthesize this whole journey. We started by recognizing that general VLMs and object detectors fail under complex constraints. To fix it, the researchers built an 80K image adversarial dataset.
Use that to train a highly accurate 7 billion parameter spatial score judge that beats models 10 times its size.
And finally, efficiently applied this judge via a top K GRPO trick, avoiding advantage bias and saving massive compute.
It is a masterclass in full-stack engineering for AI. Using targeted adversarial reward models over generalized APIs is something that should be integrated into evaluation pipelines immediately.
And I want to leave you, our listener, with a final provocative thought. We've seen that a specialized 7B model can act as a flawless spatial judge for 2D images. What happens when we apply this adversarial approach to 3D video generation?
Or to autonomous driving world models.
Exactly. If we can create an adversarial data set of temporal and physical physics violations, could spatial reward models be the mathematical link for achieving true physical world simulation?
Imagine penalizing a video generator not just for poor placement, but for having a car accelerate in a way that violates the physics of momentum.
Moving from models that just draw pretty pictures to models that truly simulate real-world physics, the implications for embodied AI are absolutely massive.
It is a necessary evolution if we want these systems to interact with the real world.
It's an exciting time to be building in this space. That's all for today's analysis. Thank you for joining us on this deep dive into the research. We will see you on the next deep dive on AI Paper Podcasts. Keep building and keep questioning the data.